Hello everyone, and welcome to another video lecture for Math 837. The topic for today is the comparison test. So let's get straight into it with a brief recap. So we started talking about series, which we defined as just an infinite sum of a sequence of elements, starting from k equals 1, or really any index. The starting index doesn't matter too much. And we take the sum of ak where the index goes from k equals 1 to k equals infinity. And then we define convergence of a sequence as the limit of the partial sums. So we said that the convergence of a series. So we said that a series converges to L if the limit of the partial sums Sn as n goes to infinity equals L. Now, instead of using the definition of convergence every time to determine if a series converges or diverges, we instead learned about a few tests that we can do. And the first of that test was the divergence test. Divergence test. And what the divergence test said was if the limit as k goes to infinity of ak does not equal 0, or it doesn't exist, then the series diverges. K equals 1 to infinity diverges. Then we talked about the integral test. Which was a way to relate improper integrals to series. So the integral test tells us that a series f of k, where f is some continuous decreasing and non-negative function, this series converges if and only if the associated improper integral from 1 to infinity of f of x dx converges. And this brings us to today's topic, which is the comparison test. Comparison test. And I should say comparison test for series because we have a comparison test for improper integrals as well. So let me start by formally stating the comparison test as a theorem. And this theorem is called, of course, the comparison test. Comparison test. Let's consider the series AK and BK. So let these be series such that 0 is less than or equal to AK, which is less than or equal to BK for all k. Then, if the bigger series, which in this case is BK, if the series of the sum of BK's converge, then the smaller series also converges. That implies that K converges as well. Now, if you recall the comparison test for improper integrals, you'll see that the comparison test for series is very similar. This should not come as a surprise because series and improper integrals are closely related. And when I talked about the comparison test for integrals, I drew a picture. We can draw a similar picture for the comparison test for series. Alright, so suppose we have two sequences, AK and BK, which are both positive, and AK is strictly less than or equal to BK for all k. And now in the same way as last time, we're going to consider the series AK as AK times 1. And the reason I did that last time is now we can think of this as a sum of infinite rectangles with height ak and width 1. So if I draw out the blue series, again, it can be anything, so I'm just going to draw random blue lines. So that represents the series AK, and of course it goes on. So the series is just equal to the area under the blue curve, or area under blue. And similarly, for BK, since I know that AK is AK is less than BK, that means the BK lines, or the red lines. So if I call this, if I call BK red times 1. So the BK lines will be on top of the red lines will be on top of the blue lines for all K. So it looks something like this. And again, it goes on. So this is area under blue. Now all the comparison test is telling us is that if the red area is finite, as in the series converges, then the blue area must be finite. So the blue the blue series, or the AK series, must also converge. Again, just like with the integral test, it's important to note that this only works if the series is positive. That's to say AK and BK are both greater than or equal to 0. In the case when they're not, we have weird things like oscillations that may happen, in which case this theorem does not hold. So let me just write that out. A red area converging implies blue area converges. So I'm going to start by doing a proper formal proof rather than just drawing a picture. So let's prove the comparison test. Proof. Okay, so let's start by assuming that the series BK converges to L. Converges to L. Goes L. Well, this by definition means that the limit of the partial sums, limit as n goes to infinity of the partial sum, and I'm going to write the partial sum as a sigma notation, so we don't confuse the partial sum for AK and BK. So the partial sum converges to L. Right. Okay, next we're going to observe that since the series is positive, so since BK is greater than or equal to 0, that means the partial sums is an increasing sequence. So this implies that the partial sum k equals 1 of BK up to n is less than or equal to the partial sum of BK, k equals 1 to n plus 1. And of course, if it's an increasing series, then each term, or increasing sequence, then each term in the sequence must be less than its limit. So this implies that the partial sum for any n is less than or equal to the limit L, which is of course equal to the limit as n goes to infinity of the partial sums. Okay, now we are going to consider the relationship between AK and BK. So we're going to leave this on hold for now. So we know that AK is less than or equal to BK. Or actually, let me also add the 0 part. We know that 0 is less than or equal to AK, which is less than or equal to BK for all K. Well, that implies that if I sum up the first n entries of both AK and BK, we'll get the relationship that 0 is less than or equal to the partial sum of AK from k equals 1 to n, and that's less than or equal to the partial sum of BK right? And from this above line here, we have that this is less than or equal to L. So we have that 0 is less than or equal to the partial sum of AK, which is less than or equal to L, the partial sum. So this tells us that the sequence of partial sums, which I'll denote as, again, I'll just leave it in sigma notation, AK of n. It's a bounded sequence. It's bounded. It's bounded below by 0 and bounded above by L. Moreover, it's increasing. It's monotonic. And moreover, it's increasing because AK is greater than or equal to 0, right? So this implies that k equals 1 due to n of AK is less than or equal to the sum of AK from k equals 1 to n plus 1. So therefore, the sequence is increasing. Okay. Increasing. So because the sequence is bounded and increasing, we can use the bounded monotonic convergence theorem, so BMCT. So by the BMCT, this implies that the limit as n goes to infinity of the partial sum, well, we know that the limit exists and it converges. Therefore, the series AK k equals 1 to infinity converges. Again, it's important to note that we can't really say just from here what it converges to. The only thing we can say is it converges to something. Okay, so let's see an example of this, the comparison test. So example, let's consider the series 1 over 2 to the k plus k. K starts at 1 to infinity. And the question is, does this converge or diverge? Right. I want to use the comparison test to determine convergence or divergence. So first thing we need to do is see if the series is positive, because the comparison test only applies to positive series, right? And we know that of one, this is a fraction, and both the numerator and the denominator are positive because 2 to the k plus k is greater than or equal to 0 for all k greater than or equal to 1, right? Both terms are positive, which implies that 1 is obviously greater than or equal to 0, so this is positive, so therefore we were working with a positive series, right? So we can actually we can actually use the comparison test. And the next step is to find a series to compare it to, right? Find a series for comparison. Right. And the series we want to find for comparison should be larger than this series if we want to show that it converges. And it should be a series that converges. So how do we make a fraction larger? Well, to make a fraction larger, I can make the denominator smaller. So what I'm going to do is, I have the denominator 2 to the k plus k. And if I want to make it smaller, I can take away one of those two terms. So I'm just going to take away the k term. So I get that 2 to the k plus k is greater than or equal to 2 to the k, right? That makes the denominator smaller for all k greater than or equal to 1. Well, this implies, if I take the reciprocal, that 1 over 2 to the k plus k is less than or equal to 1 over 2 to the k, right? And this is, of course, greater than or equal to 0. Right? So now we have to consider the series 1 over 2 to the k, right? And this series is a geometric series. Geometric series. If you recall geometric series from the previous lecture, is a geometric series with r equal to 1/2. And since well, we know that geometric series converge if r is less than 1, right? And since in this case, and since r equal to 1/2 is less than 1, the series converges. Right? So in conclusion, by the comparison test, which I'm going to denote CT, because this series 1 over 2 to the k converges, and it's larger than the original series we started with, the original series also converges. So the original series was 1 over 2 to the k plus k converges. Now, one remark I want to make with this exact same example is we found a larger series by making the denominator smaller. Instead of removing the k, we could have also removed the 2 to the k. So we could have done this. We could have done 2 to the k plus k is greater than or equal to k if I just remove the 2 to the k, which implies that 1 over 2 to the k plus k is less than or equal to 1 over k. In which case we would consider the series, we would consider the series uh, 1 over k, which is again the harmonic series from k equals 1 to infinity. And last time we also showed that this series diverges. So this diverges. So in this case, we couldn't use the comparison test to say if the original series converges or diverges. So comparison test is unconclusive. Right, so to use the comparison test effectively, you need to determine a series which converges and is greater than. And determining what series to compare it to is a matter of practice. So just like with integrals, make sure you do a lot of practice problems to really get the hang of which series should I compare with which series to show convergence or divergence. Okay, so let's look at another example. Let's look at the series k squared minus 1 over k to the 4 plus 5. And again, the question is, does this converge or diverge? We want to show convergence. Converge or diverge. And again, we want to use the comparison test. So just like before, just like the last example, first we got to see if this is a positive series, and if we can actually apply the comparison test. So again, the numerator and the denominator, so k squared minus 1, which is the numerator, is greater than or equal to 0, for k greater than or equal to 1, and so is the denominator, k to the 4 plus 5 greater than or equal to 0, for all k greater than or equal to 1. Right? Which implies that the fraction k squared minus 1 over k to the 4 plus 5 is greater than or equal to 0. Right, so again, it's a positive series. Right, so we can use the comparison test, but again, like last time, we need to find a series to compare it to, so find series to compare it. And we want to show convergence in this example. So we want to find a series that converges and is larger than this series. And generally, when you have a fraction like this, what you want to do is you want to make the numerator smaller, and the numerator larger and the denominator smaller. Right, so we're going to do that by, well, let's start with, we have that 0 is less than or equal to k squared minus 1 over k to the 4 plus 5. And the first thing I'm going to do is I'm going to make the numerator larger. And I'm going to do that by taking away the minus 1. So if I take away minus 1, I get that this is less than or equal to k squared over k to the 4 plus 5, right? make numerator larger. Right. And next I'm going to take away the 5 and to make the denominator smaller, which makes the whole fraction larger. So this is less than or equal to k squared times k to the 4, which is equal to 1 over k squared. All right, make denominator smaller. Right, so I get that 0 is less than or equal to k squared minus 1 over k to the 4 plus 5 is less than or equal to 1 over k squared. Right? So now I need to consider the series 1 over k squared. So the series 1 over k squared, k equals 1 to infinity. Right, this is a p series, which we covered last time, so it is a p series. And we know by the p series test that this converges because p is greater than or equal to 1. In this case, p is 2. So it's a p series which converges by p series test, since p equals 2 is greater than 1. Right? So therefore, since this larger series converges by the comparison test, our original series converges. Right, so that was 2 examples of how we use the comparison test to show a series converges, but we can actually use the comparison test to show a series diverges as well. And to do that, we need to talk about the contrapositive of the comparison test statement. So let's consider the contrapositive, or actually let me just write it down. So the comparison test said that if 0 is less than or equal to ak, which is less than or equal to bk, then the larger series convergent, k equals 1 to infinity. If the larger series converges, this implies that the smaller series converges. Now what's the contrapositive to that statement? Well, the contrapositive is that if ak is a contrapositive, the contrapositive is again if 0 is less than or equal to ak less than or equal to bk, if the series ak does not converge, or in other words, the series ak diverges, so 1 to infinity diverges, well then that implies that the larger series bk also does not converge, or diverges. bk from k equals 1 to infinity diverges. And if I go back to the picture that I drew, we can see this pictorially as well. So if the red area being finite implies the blue area is finite, well then if the smaller blue area is infinite, or the series diverges, then the red area must also be infinite. So in this way, the comparison test can be used to show both convergence and divergence. So let's see an example where it's used to show divergence. So example, let's consider the series k equals 1 to infinity of k over k squared minus cos squared k. And we want to show that this diverges using the comparison test. So again, we should check that the hypothesis or that the series is positive, so the comparison test can be used. And that's easy to show because we have that cos squared k is less than or equal to 1, which implies that k squared minus cos squared k is greater than or equal to 0 for all k greater than or equal to 1. And then this is of course the denominator, and the numerator is just k, which we know is greater than or equal to 0, so that implies that k over k squared minus cos squared k is greater than or equal to 0 for all k greater than or equal to 1. So now we can find a series to compare this to, and since we want to show that this diverges, going back, we want to find a series which is smaller than our given series, and that diverges. So in this case, we want to make this fraction smaller. Again, how do we make a fraction smaller? Well, now we can make the denominator a bit larger. So in this case, we'll remove the cos squared part. So we have, to do this formally, we have that cos squared, minus cos squared of k is less than or equal to 0, which means that k squared minus cos squared k is less than or equal to 0, less than or equal to k squared, less than or equal to k squared, which implies that 1 over k squared minus cos squared k is greater than or equal to 1 over k squared. And then we can multiply the top and the bottom by k, the left and the right hand side by k. So then k over k squared minus cos squared k is greater than or equal to 1 over, or k over k squared, which is equal to 1 over k. And 1 over k is, again, a positive series, as a comparison test demands. Right, so to put it together, we have that 0 is less than or equal to 1 over k, which is less than or equal to k over k squared minus cos squared k. Right, and this time we're looking at the intermediate, or the smaller series, which is just 1 over k, so the series 1 over k. Right, this series is the harmonic series again, and we know that the harmonic series diverges by the p-series test. Harmonic series diverges again by p-series test. Since p is equal to 1, right? So this implies that by the contrapositive statement of the comparison test, or you can just state by the comparison test, therefore by comparison test, since the smaller series diverges, the original series we started with, which is k over k squared minus cos squared k, right, this series also diverges. Now I'm going to finish this off by talking about something called the limit comparison test, which is very similar to the comparison, or it's related to the comparison test, but it's more general. But you won't be responsible for this. So the limit comparison test. So I'm stating this, but you won't be responsible for it. Comparison test. So you're not responsible. So theorem. What the limit comparison test tells us is that, suppose we have two series, so let AK and BK be series.
I'm here.
Sorry, the word series triggered my phone, but let AK, BK be series. Then the following is true. So one, if the limit as k goes to infinity of AK over BK is equal to L, where L is greater than 0, it's a real number, then either both series converge or both diverge. So either both series converge, or diverge. Or in other words, AK converges if and only if BK converges, diverges. Okay, 2. If the limit as k goes to infinity of AK over BK equals 0, and sorry, I should really point, it's important that I point out AK and BK both have to be positive series for this to work. So their limit can either be a positive number or it can be 0. In this case, the convergence of BK equals 1 to infinity implies the convergence of AK. Implies k equals 1 to infinity of AK converges. Okay, and thirdly, the limit, if it's not 0 and if it's not some non-zero real number, then the limit must be infinite. Because again, we're dealing with a positive series, so it can't be negative. So if the limit AK over BK is equal to infinity, then the divergence of BK, so if k equals 1 to infinity of BK, diverges. This implies that k equals 1 to infinity of AK diverges. So again, this is a lot more general. It can come in more handy, but you're not responsible for this for the limit comparison test for this course. So that's where I'll stop today. Thanks for watching. And again, I have office hours on Piazza Thursdays from 11 a.m. to 1 p.m. if you have any questions about anything in this lecture. I also follow Piazza regularly, so if you ask a question outside my office hour times, I can probably get back to you as well.